In the last lecture, we were discussing about the convergence of sequences, and we had stated a result that if x n is a monotonically increasing sequence which is bounded above, then x n converges. Similarly, if x n is a monotonically decreasing sequence which is bounded below, then it converges. Basically, in the first case when it is increasing, one can show that this x n converges to the supremum of x n, because it is bounded above by the least upper bound property. There exists supremum, least upper bound exists, that is the supremum of all the set x n, and this increasing sequence will converge to that just by the definition of supremum. Similarly, if it is bounded below, then in greatest lower bound will exist and this x n will converge to that. So, let us see one example based on this result. Let us take our x n example. X n is equal to 1 plus 1 by n to the power n. Now, first let us try to see that, I mean, whether this is monotonically increasing or monotonically decreasing. So, our first claim is that this is a monotonically increasing sequence. So, let us try to write it down. This is equal to, we know how to expand this by binomial theorem. So, this is 1 plus summation over n choose k, and then 1 by n to the power k into 1 to the power n minus of k. So, this is, we can remove this one, this is k is equal to 1 to n and plus k equal to 0 term, I can put it as 1. Okay. So, now this is 1 plus summation over k from 1 to n, n choose k is n into n minus of 1, this goes up to n minus of k minus of 1 into k factorial goes up into n minus of k factorial, this is k factorial, and then 1 by n to the power k. This is equal to 1 plus summation over k from 1 to n, 1 by k factorial, and now if I divide, these are in the numerator, there are k terms. So, if we divide n in each of the term, what we are going to get is 1 into 1 minus 1 by n, this goes up to 1 minus k minus of 1 by n. Now, n is less than 1 by n, n is less than n plus 1. Therefore, 1 by n is greater than 1 by n plus 1, and minus of 1 by n is less than minus of 1 by n plus 1. So, this entire thing is less than 1 plus summation over k from 1 to n plus 1 by k factorial 1 minus 1 by n plus 1 in each of the term k minus of 1 by n plus 1. So, this if you write it down, then this is going to be equal to x of n plus 1, that is 1 by 1 plus n plus 1 to the factor of to the power n plus 1. So, this is a monotonically increasing sequence. Now, if we can show that this is going to be a bounded function, a bounded sequence, then by this theorem what we can conclude is that this converges. Now, look at this, x n is equal to this 1 plus k equal to 1 to n 1 by k factorial 1 minus 1 by n up to multiplied up to 1 minus k minus of 1 by n, and each of these term 1 minus 1 by n 1 minus of k minus of 1, they are all less or equal to 1. So, therefore, x n this is less or equal to 1 plus summation over k from 1 to n 1 by k factorial 1 into 1 into 1. So, that is equal to 1. So, this is less or equal to 1 plus summation over k from 1 to n. So, this is 1 into k fact 1 by 1 into 2 into 3 up to k. Now, after 3 is greater or equal to 2. So, each of these term are greater or equal to 2. So, this is equal to, this is less or equal to 1 plus summation over k from 1 to n 1 by 2 into 3 is less or equal to 2 into 2, 1 upon 2 into 3 is less or equal to 1 upon 2 into 2. So, like this. So, this what we are going to get k minus of 1. So, this is equal to 1 plus 1 by 2 or this is equal to 1 plus 2 times summation over k from 1 to n 1 by 2 to the power k. And we know that this is a geometric series which is going to converge, which is a finite number. So, this is less or equal to, one can show that this is less or equal to 3. So, therefore, this sequence x n equal to 1 plus 1 by n to the power n is a monotonic sequence which is bounded above. So, definitely what we know is that this limit of this sequence exists, that means this sequence converges. Wherever it converges, let us call that number to be E. So, from this we conclude x n converges. Define limit n goes to infinity 1 plus 1 by n to the power n is equal to E. This is what is one definition of E. Okay. So, this is a nice example. So, now what we have seen is that every sequence which converges has to be bounded, but every bounded sequence does not converge. For example, what we have taken the sequence we have seen like this. So, now this is what we have done is minus 1 to the power n minus of 1. So, if n is odd, that is x 2n plus 1 if we take, then this is going to be 1, because 2n plus 1 minus 1 is 2n, minus 1 to the power 2n is always going to be 1, and x 2n, this is always going to be equal to minus of 1. Now, if I define a sequence y n equal to x 2n plus 1, again this y n is going to be a sequence, and this y n being the constant function 1, this converges. Similarly, if we define z n is equal to x 2n, then z n is equal to minus of 1, constant sequence minus of 1. So, this is also going to converge. So, although the entire sequence may not converge, but there is a part of the sequence which contains infinitely many numbers, which we put it in the form, like for example, y 1 is equal to x 3, y 2 is equal to x 5, so on and so forth. So, this is the part of the sequence x n, this converges. So, is it accidental, or we can say something like this happens to almost all bounded sequences? As a matter of fact, what we are going to state is that this phenomena is true for all bounded sequences, and in order to write it explicitly, so what we need is to define a concept what is called a subsequence. So, subsequence is essentially you can understand that this is a part of the sequence, but in the sequence this is not just an infinite set. What it is that you have a preferred order for each of the seat, which is going, you are putting it as an increasing number and you are assigning a number to that. So, that we have to take into consideration while defining this particular type of subsets of a sequence. So, let us define what is subsequence. Let I will define n choose k, k from 1 to infinity. This is contained in n, set of natural number, such that n k is less than n k plus 1. So, that means what? So, what I am doing is that suppose I have taken 1, 2, 3, 4, 5, 6, right. So, I take n 1 to be 2, this is equal to 2, n 2 to be let us say 5, n 3 I will take to be equal to 9, n 4 I can take to be equal to 31, like this I go on. So, n k plus 1, whatever the number I choose, I do not have restriction, but it has to be bigger than n k, previously chosen number position. So, that is what is, suppose for example, another was I will take n 1 to be 2, n 2 to be equal to 4, n 3 is equal to 6, n 4 is equal to 8, like this. That means n k is equal to 2 k. So, if I take, then obviously this satisfies this condition. So, these are all the examples. So, now given a sequence, x n, n equal to 1 to infinity, a subsequence of x n is given by x n k. It is an infinite number. So, not necessarily all these x n's are there, it can have x 2, x 4, x 6, x 8. So, this is a subsequence x n k. So, all these n k's are natural numbers and this satisfies that n k is less than n k plus 1. So, this is the example, particular example of the subsequence. So, what is one of the most important result about the convergence of the sequence, which we will not prove, it is called the Bolzano-Weierstrass theorem. So, this states that any sequence, any bounded sequence has a convergent subsequence. So, if you give me a sequence which is bounded, it may not converge, but I can always produce you a subsequence from that sequence which is going to converge. For example, what we have seen is that minus 1 to the power n. If we take the subsequence to be 2 k, then obviously this subsequence is going to converge. That is the Bolzano-Weierstrass theorem is saying, that every bounded sequence has a convergent subsequence. Anyway, as I said, this is a fact which I want you to know. I am not going to give you the proof for this, neither I am going to use this in my further lectures, but this is very, very important fact in the convergence of sequences. Also, I mean, this will be interesting to ask that what are the criterion for which, I mean, if we check that criterion, then we can definitely say that this given sequence is going to be a convergent sequence. Of course, it is, if it is monotonically increasing and bounded above, then the sequence converges, but not all the time this is going to be a monotonically increasing and bounded above. So, this is the concept of the Cauchy sequence comes in. So, what is a Cauchy sequence? Just think that suppose from various parts of India, people are coming to an institute. Someone is coming from the south, someone is coming from east, someone is coming from the west of the country and far north of the country. So, suppose they are coming to an institute which is located in central India. So, while all of them where they are converging to the point, to the institute, simultaneously what with the passage of time, the distance among themselves are becoming smaller and smaller. Finally, they will converge to a point. So, now suppose if someone is coming from here, someone is coming from this direction, someone is coming from this direction, while approaching to the point here. So, their distance, suppose at 5 hours before they were here, then the distance between them, whatever the distance between them, and after 5 hours if they are here, their individual distance are also becoming smaller and smaller with the passage of time. Now, if they converge to a point, then this is going to happen intuitively. One may ask that if this phenomena happens, will it necessarily be true that they will converge to a point? So, that is the concept what we are going to deal now in this form Cauchy sequence. A sequence x n is said to be a Cauchy sequence if for every epsilon positive there exists n naught belongs to n such that mod of x n minus of x m, this is nothing but x n is a number and x m is some number, x n minus x m is the distance between x n and x m, you can think of it, is less than epsilon whenever both n and m they are greater or equal to n sub naught. So, this is so which means they individually they are coming closer to themselves. For example, so now suppose you have 1, 2, 3, 4, 5, 100 like this. So, your x 1 is here, x 2 is here, x 3 is here, x 4 is here, x 5 is here, x 6 is here, something like this, you are going x. Now, what it says, the Cauchy sequence it says is that you take any epsilon, then after n sub naught you are going to get n sub naught. So, now you take, you will find a band epsilon distance from here to here, where all these sequence x n and x m whatever we are going to get are going to lie in this. That is what is the concept of the Cauchy sequences. So, one of the fundamental result which is equivalent to the least upper bound property of the R, which we are not going to prove, that every okay. So, one can see that if x n easily, if x n converges to x naught, then x n is Cauchy. Why? Because you take x n converges to x naught, that means x n minus of x naught is less than epsilon by 2 for all n greater or equal to n sub naught. Now, you have x n minus of x m, this you can write it by triangle inequality plus x m minus of x naught. Now, if n is greater or equal to n sub naught, this is less than epsilon by 2. If n m is greater or equal to n sub naught, this is also less than epsilon by 2 for all n m greater or equal to n sub naught. So, every bounded sequence is Cauchy. Now, is it true that every Cauchy sequence is bounded? As a matter of fact, this is also true. So, major result converges. That is this is one of the most fundamental result, and there are various ways you can check that what are the condition in which we can test that the sequence is a Cauchy or not. So, we will not spend more time on the Cauchy sequences now. If we need to look for the criterion of the Cauchy sequences at a later stage, then we are going to discuss it there. So, thank you.